PST. Welcome, everyone. So for those of you who don't know me, my name is Antje Bart. I'm actually located here in Germany, so for me it's 6 p.m. Chris asked me to kindly host the call today. So welcome, everyone. Thanks for joining us. And we do have a packed agenda, so without further ado, I would like to introduce Dave Nielsen, who will present today about Redis data structures and Redis streams. And Dave, the floor is yours.
Great, thank you very much. Can you hear me okay, and can you see my slides?
Yes, we can hear you and can see the slides.
Okay, great. All right, so hello everyone. I'll just jump right in. My name is Dave Nielsen. We're going to talk about Redis streams, and I'll start off with a quick introduction to Redis, and then we'll get off into some use cases and go through and explain what Redis streams is and how it works. All right, so very quickly, you probably already know about Redis. It's an extremely popular open source database. It's usually used in memory, and basically what we mean by that is that Redis can be used in memory only where there's nothing saved on disk at all, and then it can also be used as a persistent data store where the data is stored on disk as well. The thing about Redis that makes it unique is that it's never actually reading from disk. So in other words, even if the data gets put on disk, there's always the same data in memory. And so when you're reading from Redis, you're always reading from memory. And that combined with its data structures makes it incredibly fast. So then I work for Redis Labs, which is a company that's behind Redis. So we employ Salvatore, the creator of Redis, and we have our own cloud-hosted product as well as software that you can use that is sort of like a management-focused Redis enterprise software. And if you want to, you can follow these URLs and you'll get a hold of the enterprise software or the cloud. And I just want to mention that we do have a 30 megabytes of free usage on our Redis cloud. There's lots of companies that use Redis. You probably already know this, but it started off on Twitter and then caught on Heroku and then just basically took off from there. And its differentiators are this crazy fast. It's got very simple data structures that all have their own specific performance-oriented objective and use cases. And it has modules where you can extend the functionality of Redis as well. So you basically build new data structures or even new databases on top of Redis. It's used in lots of different examples, but what I'm here to talk to you about today is the data stream or the streaming use cases. So it's already been used for job queues and messaging and notifications and fast data ingest and time series data. And now with Redis streams, we can make some of that or even all of that better. But before we go any further, you have to understand one thing about Redis, and that is that it's not like one database that has one type of data structure and you do one thing with it. Like a SQL database, you do SQL. With a document store database, you might do JSON documents. With a graph database, you might do graph. Redis has lots of different data structures, and each one of them are incredibly fast. It's all written in C. It's all in memory, and I just want to share a couple of these with you before you get going. But streams is the most recent one to be added about a year ago, but it had been in GA for pre-beta or pre-launch for a long time, so you could. It's very, very reliable. Yeah, so these different data structures give you things like caching SQL queries, storing ones and zeros in a big giant bitmap so you can know who's online or offline immediately, storing larger numbers in one key, hashes for things like user sessions, lists for using stored data in the order they were received, like a queue, sets for storing unique values, sorted sets for storing things like a leaderboard where you need a key, like a username, and then the value, which would be their score, and you can have like millions of these things in memory at one time. Geospatial indexes, which is what you might use to build an Uber or Lyft mobile app, and you see the cars moving around. Hyperlog, which stores probabilistic data. It's not 100% accurate, but you can store terabytes of values, basically about 12K of memory. And streams, which is what we're here to talk about today. Okay, so first, for those of you who've never used Redis, it's crazy easy. All right, quick. A cache. I want to go get my key in memory. Oh, it's not there. Let's go and get it from my SQL query and take that value and then set my key equal to the results of that query and have it expire in 5 seconds or 5 minutes. And then let's, in the future, go get my key, go get my key, go get my key, and then in 5 minutes it'll expire, and then you'll do the whole process over again. Very, very easy way to scale out. Another very easy way to scale out with Redis is to use Redis as your user session store. So store all your user sessions in memory. This is another great way to scale out your web application. So for more on caching, just go to redis.io, commands set, and you'll get that. All right, so let's get into it. What is a data stream? So I think many of you already know this, but I'm going to go over it very quickly. So you've got a producer that's sending data to your server, and you want a consumer to get that data. So this is great. You can even scale out kind of this way. It sort of works where you have lots of producers sending data to a stream, and then you have lots of consumers pulling from that stream. But it's actually a lot more complex than that, as many of you probably know. And so let's figure out exactly what we want to do here. All right, so the first step is you've got your stream getting sent to the server, and you're going to transform that data into the format that is required, and then you can output that into a stream, and then you can do something with that data. All right, so good news. Streams gives you all of this, except for the analytics part, but that can be done with other parts of Redis. But I also want to point out that Redis has already been doing some of this, either via PubSub or lists or sorted sets. A lot of people use PubSub actually for this kind of thing, where you want to send information to a bunch of clients that are subscribed to that information or to that channel, and that works pretty well. Except for with PubSub, it's a sort of a fire and forget. Okay, I'll skip this demo right here. I'll come back to it in a minute. Oh, hold on a second. Let's move past this. Okay, there we go. All right, so let's go understand Redis streams. So first, let's look at the challenges. You've got a producer or producers creating a stream, and you have a variety of consumers. All right, so those consumers may or may not be receiving that data in the same at the same time or in the same speed. Okay, some might be getting it real time, others might be looking it up periodically, and others might just only be looking it up, for one time. Back up. All right, so here's an example of the catch-up problem, where you've got your producer generating a bunch of records, maybe 500 per second, and you got into your Redis stream. So those records are piling up there, and you got your image processor, which cannot handle that at that speed. So it starts to back up. So you got your fast, slow, and you got your backlog. And so you can add 5 or more clients to consume this, and then that catches you up. All right, pretty good so far, right? That's called scale out. However, what happens if one of those fails? You have, well, first you have the mutually exclusive problem where you don't know who's getting what. And then you also have a failure scenario where something goes down and you don't know if they've consumed the data or not. So how do you recover from that? So with, or you might also have the problem where your producer crashes and comes back up. So how do you handle all this? So with PubSub, like I said before, it's more of a fire and forget. And so if your clients fail and they are not able to receive the information in real time, then they're not going to receive that information at all. That can be a problem. And then we have lists and sorted sets are also ways you can do streams, but a stream-like behavior, but I'm just going to skip that right now. And so what streams allows you to do is to asynchronously exchange data between a producer and consumers. So you might have 3 consumers, or you might be doing image processing, or 3 different consumers, or you might have 1 consumer, but you need to replicate it so it can keep up. And so what we're going to do with Redis is we can actually have multiple producers generating a stream using xadd as the, that's the command. And then you can do xread group to read from that group, or just read from a stream if there's no groups. And you can pull the data out. And so in the example at the bottom here, you just have 3, each individually pulling data, and they're not really coordinating with the others, whereas in the consumer group, you can actually have them coordinate. So here's all the commands. There's not that many commands for Redis. I strongly recommend you check this out. There's a Getting Started blog post up on redislabs.com, and it'll go through the different commands. There's not that many, so not that much to learn, at least to get started, and then it gets a little more complicated. So for example, we've got xadd and xread. So xadd is how you add to the stream. Xread is how you pull from the stream. Here you've got a stream being created. You can set to how many you want to pull down at one time. And you can also just specify whether you want to start from the beginning or just pick up anything new. That's what the $ is anything new. All right, so then you can also pull a range of values by specifying the timestamp start and end. You'll notice here there's a long digit with a dash and then a 0. And that dash and the 0 is basically anything that's sub-millisecond. You could end up with a problem where you end up with the same timestamp. And so what Redis does is anything that gets generated, if there's more than one value that gets generated within a millisecond, it will then start to increment that, so you will never have complete duplicates if you include the -0, -1, etc. Count 10 will pull in 10. And then here you got x range MyStream plus and minus plus. That means start from the beginning, go to the end, but only give me up to 10 at this point. Okay, so that's basically how one Redis stream will work. If you want to work with a consumer group, then you're going to do the same thing, except for you can use xgroup instead of to specify the group name or create a group. And then you're going to read from the group. And then because the idea of consumer groups is that you can have multiple clients coordinating together, you want to make sure that you acknowledge that that you've received that record and have processed it. And then if the record is not processed correctly, or if you go down, you've never provided an acknowledgement, then another consumer can actually claim the pending records. And so this is one of those cases where you might have a consume at least once scenario. Okay, so it looks like we have some questions here. I'm not sure exactly where to go. There's some in the chat here. Okay, let's see. Please provide more concrete examples to let you know what a stream is. All right, so yes, I'm gonna answer that in just a moment. So let me come back to that. Here, let's do this. Let me give you this example here. So streams, there's lots of examples. There's 2 examples we're showing you here. One is we've got let's say a message that's being sent from 2 users. Maybe you have a chat or something like that, and you want to be able to make sure that the system is scaling and that all of the consumers of that chat are getting the message. So you don't necessarily want to do a fire and forget, which is what you could do with PubSub. You may want to have a stream, which may be very short-lived until all of the clients receive the information. But what's happening is that chat message that somebody sends, for example, like the one you sent, is going to be stored in the Redis stream until all of the clients that have subscribed to that particular stream receive that information. In fact, it may even live longer than that, depending on how long you specify you want to retain the data. And so in this particular case, we have a messaging app receiving the messages, but then you might want to, behind the scenes, be analyzing information for spam or for perhaps inappropriate language. So you may be doing something in a different stream which they're not coordinating. They're just both pulling down the information. And you might try to decide if there's some inappropriate images or something like that being shared. So that's a different stream. And then you might also have a backup where the data is being backed up. So you have a retention policy or something like that, and that'd be a third stream. Or in this particular case, we have an example where we're diving into one of those streams and we're actually having multiple clients. So I think I'm going to run out of time here, so I better be careful. There's more chats here. Let's see. How does Redis handle the stream backing up? For example, 500 with 500 stream could have thousands of samples after just 5 minutes. That is correct. So Redis is, of course, limited by the amount of memory you have. So you better have a lot of memory if you intend to process a lot of data that could be backing up. That is absolutely true. And so the problem there is that you might want to have lots of memory. You also might want to use Redis on Flash, by the way, which is a Redis enterprise product. You can actually go up to terabytes of data in quote-unquote memory, where we use Flash as a memory extension, where the keys get stored in memory, but the values are stored on Flash, or you actually have a little slider. You can kind of adjust that. But yes, that is an issue, and you need to be aware of that. Just like your disk, your hard disk filling up, you got to be aware of when your hard disk might fill up. All right, and so if expiry is not defined in Redis, then it will stay in memory forever. Yes. Now, the Redis does have different ways in which you can expire data. So, in fact, there's quite an extensive variety of ways in which you can expire data. So you might have it expire that it stays in memory, but if memory fills up, then the oldest data will get deleted, and then that way the new data can be staying in memory. Yes, so there is lots of different ways in which it'll handle that, but you should be concerned about having your data be lost in memory if you don't take care of that. Okay, I'm gonna keep going here. All right, so I already passed this, so let me keep going. All right, so we're just going through examples here of how you can, create a group. You must create a group. Redis doesn't automatically create groups for you, but once you created your group, it's there. You can use it. And here's an example of where you're reading from a group, and you're particularly specifying a stream, because there can actually be multiple streams that you can read at one time. This is just for efficiency's sake. So if they have multiple groups and multiple streams, you want to specify all of them. And here you're pulling down the data into Redis. And again, here's another acknowledgement saying, okay, I've received that record or this range of records. So you can go ahead and tell the other clients not to use them or request them. And so I'm going to keep going here. So how do you claim the data? So once a client goes down, a consumer goes down, and it's no longer receiving the data, it may have pulled the data down, but it didn't actually tell you that it received it. So another client can now claim that data and then process it in case it hadn't been processed the first time. And so in this case, you got to be careful that you're not, you recognize that it is possible to process the same record twice. Okay, and so here's an example where you're taking a pending record and claiming it so that you can process it and make sure it got processed. Okay, I think there was another question, and I think I'm running out of time here. So let me see what the last question is. Will all this get recorded? Okay, and Auntie will answer that question. All right, and just about done here. Okay, so very quick, I just want to show you, I think I can, I might have to reshare, so hold on one second. So let's go ahead and share. And let's just do the desktop. Okay, and over here, all right. So here I have an example of a Java application, and we have a collector. Let's see, here you go. We have a Twitter ingest stream, so that's pulling data. You can see this data actually being pulled down from Twitter, okay? And then we have a, let's see, where is it? An influencer collector that's being, where it's collecting the data. And let's see if I can find this right here. Here we go. Okay, and it's not only collecting it, it's looking at each record that comes through. It's looking at the producer of the tweet, so the Twitter account, and it's checking out to see if they have how many followers they have, and if it has more than 10,000 followers, it adds it to a different stream. And so now we can have a stream where we're collecting. In one stream, we're collecting all the tweets and passing them on or letting them be consumed. And then in another one, we're creating another group and stream, and we are only putting the number of, putting in here the information where it's the Twitter accounts that have over 10,000 followers. Okay, so it's just a very simple example, but one you can see. And then I have also, here's an example of the app. Here you can see this stream is being generated. We're up to 43,000. That's basically the duration of this demo. And all these are going into Redis. And then here's the new influencers being added. Out of the 43,000, we now have 984 influencers that have, or tweeters, that have over 10,000 accounts, or followers, sorry. Okay, and we even have a little top demo here. All right, so here's where we're using a combination of Twitter streams and PubSub. The PubSub is pushing the data down to the client in the browser. Okay, we're going to go back to my presentation here. Hopefully you can see it. All right, so there's lots and lots of use cases. Media use cases are obviously very popular, where you've got Redis streams like the demo I just showed you. And if you want to try out Redis streams, there's now lots of support by different client libraries, whether it's Java, Python, JavaScript, .NET, Go, C, PHP, Ruby, etc. You can go to redis.io and /clients, and you'll be able to see the client libraries. And here, these are the ones we know there is Redis stream support for. So at that point, I'm going to go ahead and end this and see if there's any more questions, and then we can move on to the next speaker.
Yes, thank you very much, Dave. So if anyone still has questions, please put them in the chat window here. And yes, the recording will be shared afterwards. And maybe just a quick shameless plug, there's a workshop coming up this Saturday, I think, a whole day workshop in Santa Clara. So where we'll have Dave again and focusing a little bit more on image recognition using PyTorch, TensorFlow, and Redis as well. So if you want to spend more time, please check out the link that I just posted and register for the upcoming workshop as well. All right, and with that, thank you very much, Dave. And I'll hand over to Morten. Let me see, Morten, can you hear us?
Yeah, I'm here.
Yes, perfect. So welcome to today's call. Morten, you're gonna introduce us to TensorFlow Encrypted, I think, correct?
Yeah, that's correct. Can you see the screen now?
Yes, we can see. Stage is yours.
Oh, thank you. Yes, hi everyone. Thank you for being here. So I'm going to talk about TF Encrypted. It's one of the side projects, or one of the open source projects we're working at DropOut Labs for basically doing machine learning on encrypted data. So I gave you a quick walkthrough. I don't have a demo, but there is a lot of examples on the website that you can go and play with. So the first question is why do we care about privacy in machine learning? And one way of framing that is basically to say that if we look at the normal machine learning process, we can run into some bottlenecks, some issues with this process when we start to deal with sensitive data. So the normal machine learning process might look like this, where we start by having a data set we collect on the server, we run it through a training process, and then we develop the prediction service. And then, of course, that exists in a context as well. where we might ask, how do we get this data set? Well, it could be internally generated data, but often we will also have to go to external parties and ask them for data. It could be experts or specialists that are somehow willing to contribute the data. It could be data we go out and buy for a certain price and so on. And likewise, when we have our prediction service, we also often want to use that as an external service and offer it, for instance, to a client over here that can send new data to the service, run it through, and get back a prediction. Okay, so one concrete example for when we start to introduce sensitive data, and this was a use case that was presented by a group of researchers about 2 years ago at the TensorFlow Dev Summit. What they did is they developed a skin cancer or skin lesion detection system. So there's this mobile app, you take a photo of a skin lesion, it runs through convolutional networks, and it gives you back a prediction about whether or not you should have it further inspected. The way they built that system was they went to a lot of dermatologists, they gathered this large set of clinical photos, they ran it through a transfer learning, and then ended up with this convolutional network. And what they managed to reach was actually expert level prediction. So in other words, everyone with a mobile phone would now have an expert dermatologist in their pocket. So at the fear of stating the obvious, it's kind of clear that as soon as we can start to apply machine learning on sensitive data, it's going to have a huge impact on healthcare. But there's also some issues in this. And as I said, one way of framing this is in terms of the bottlenecks that could exist when we're trying to build a system like this. And the first one is, how do we get access to this data? So there could be some liability issues for instance, from the dermatologist we just saw. It could also be that the company, they're willing to sell the data, but since they don't know how, since they can't control how the data is being used, they're going to charge a price that a company or a group of people that want to build a service simply cannot afford. Then there's also an issue of saying, even if we do get the data, we could potentially face a huge risk by actually just holding on to this data because it is sensitive. So if someone were to break into the system or otherwise leak the data, we might be in trouble. If we do manage to build our prediction service, we're still not done yet because we also need to incentivize users to actually use the service. So if you're potentially telling a company whether or not you have skin cancer whenever you use their service, it's not clear that you would use the service in the first place. And then finally, we might also want to control the leakage that actually happens back through the predictions when we send them back to the client. So this is both of the original training data, but also the model that could represent significant IP value to the company. So one approach you might have heard of is kind of standardization process using differential privacy, where we're adding noise to the process in the hope of this is going to, we can actually make some strong guarantees that this is going to hide any personal data in the data set. The way it works is that we can sanitize the data sets. We can then train on it without fear, and we can then use it for predictions afterwards that can also be sanitized in making sure that they don't leak too much about the model. This takes care of risk management. It also takes care of leakage. However, it's not clear that people are incentivized. It's not clear how you can do this and still have good accuracy in the predictions you do if you use this process. And it might also, even if we can sanitize the data set, we might actually remove a lot of the signal that we were using, meaning that the data set is less interesting than it was before. So we might not be able to build the service. An alternative approach that I'll be talking about today is where we use encryption. And this is not encryption in the classical sense. This is encryption where we can compute on the encrypted values while they remain encrypted. So if we do this, then the data set we get from the external parties is encrypted. It remains encrypted while we're doing the training, and we can also do predictions afterwards on the encrypted data set without being able to decrypt at any point. So that takes care of risk management because we're only storing encrypted data. Users are also incentivized because they're the only one that can decrypt the final result. However, it doesn't do anything about leakage because we're running exactly the same thing as we're running before. So whatever leakage there was without using these techniques, we'll also have now. But assuming we can somehow get around that, then we can also deal with data access from the data providers because they can be part of this process and they can determine how the data is being used. Okay, so to give you, so we can also mix the two. So we can have this hybrid approach where we're saying we're both sanitizing data and encrypting the data. And if we do that, then we can get around the last few items as well. Then we can start to control the leakage of our data set. Okay. So just to give you a quick idea of how computing on encrypted data works, I don't want to go too much into cryptography. I just want to give a very quick overview so you have some intuition about this stuff. Let's start with a very simple model, and now we want to market prediction. So we're going to use a linear model, meaning the client is going to send over his X, and then we're going to compute the dot product and send it back to the client. If we just state the formula for this, or write out what the dot product is, we see we have two vectors, x with 3 components and w with 3 components. We take the component-wide multiplication and then we add everything up. Then we end up with a scalar value, which we send back to the client. Now this is doing it in plain text. And now if you want to do it on encrypted data instead, one way of doing it is to use something called secret sharing. And secret sharing essentially takes the data and splits it into 2 shares. And if you only see one of these shares, then that share doesn't leak anything about the data itself. So in other words, the cloud service we have up here, the prediction service, it now sees the share 1 of X, but that doesn't leak anything about X. And I'll go into details about why in a bit. And we also have a helper now. So we have a helper down here at the bottom, which is now receiving the 2nd share of X. But again, seeing this on his own, he can't learn anything about X. However, they can now go into a protocol, so they can do a collaboration with each other, computation, to arrive essentially at a share of the dot product. And again, they don't know what the share is, but they can send both of them back to the client. Now knowing both shares of the dot product, the client can reconstruct and get his prediction. So if we put into the formula from before, and we start to, and we type it out a bit more, we can see that we need to perform 2 operations. So the first one was we have a share of a value, and we want to multiply it by something. So let's say we have a share of x1, and we want to multiply it by w1, and essentially move that w1 into the sharing. If we can do that, then we say we can do a public multiplication. Then if we do that for every component, we're going to end up with shares of x1, w1, x2, w2, and so on. And now we want to add these up. And then we say we can do a private addition if we can do that. Then we end up with basically a share of the dot product. And what we need in order to have these 2 operations is what we call a homomorphic secret sharing scheme. Let's see what some scheme like that looks like. So here we have something called additive secret sharing. We're sharing a value x using some randomness r. And the first share of this is just r. It's just a randomness. So if we see just this, then of course we don't see anything. We don't learn anything about x. And the second share is x minus r. And again, this, if we don't know r, so if you don't know the first share, then this x minus r looks completely random as well. But of course, if we know both, then we can add them together. The r cancels out and we get back x. As a quick example, let's say our modulus is 10. We want to share 5 using randomness 7. Then the first share is 7. The second share is 5 minus 7. So that's minus 2. Minus 2 mod 10 is 8. So we now have the 2 shares. We can add them back together again. That gets 15. 15 mod 10 is 5, which was our original x. Okay, so the first operation we had to do was private addition using these secret sharing. So we have the 2 servers now. We say they already have a sharing of x, they already have a sharing of y, and now they want to have a sharing of x and y without learning x and without learning y. Turns out they can just add what they already have. So we can define the set 1 and the set 2 in this way. And if you rearrange the formulas a bit, you can see that set 1 and set 2 now adds up to x1 by x plus y. And the second operation we had to do is we had to multiply with this w. So let's say we have a sharing of x and both parties knows w. Then again, they can just multiply what they already have, and we can rearrange, and we can see that this set 1 plus set 2 now adds up to x times w. So in other words, we can build a private prediction service for a linear model using what we already have now, and without any of the 2 parties learning anything about the client's input. But of course, we can also go a bit further, because now the cloud service, as we saw it, it had to reveal to this helper at the bottom the W that was being used in the model. And if it doesn't want to do that, if it wants to keep this W private as well, because it might represent significant intellectual property, then of course we can also secret share this W. And then the only thing that changes now, if we look in our formula, is we have to do, instead of a public multiplication, we now have to do a private multiplication. We can also do that using our secret sharing scheme. So let's say we have an X and a Y here. Now, I don't want to go into the details because it's a slightly more complicated protocol. The important thing is, when we want to do this, we need to have some communication. So this is where the 2 parties have to communicate with each other. And then we also need to use some other material. You can run through this if you're interested. The key thing here is just there needs to be some communication, but then we can also do private multiplications. Okay, so this was all just to give you a quick idea of this is not completely magic behind the scenes, but also to illustrate that when you want to build these systems for encrypted machine learning, you start to mix a lot of different fields together. So one is cryptography, where we have various techniques, protocols, and trust that we can use, trust assumptions. We have machine learning, where we can see, okay, what are the right models to use in the encrypted space? How can we optimize them in terms of performance? What kind of precision do we need? That can also have an influence on the runtime performance. We also have a large software engineering efforts to do, because we're now building these distributed systems where some of the parties need to communicate. We need to take advantage of the multi-core architectures and so on. And finally, we also have questions on data science, saying what are the right use cases right now that fit within the encrypted paradigm? How does it affect our data science workflow when we start to only see encrypted data? How do we do feature engineering? How do we do monitoring when we put stuff in production and so on? And our basic assumption is that if we manage to create some kind of common framework for these groups of people, then we can help push the field of privacy preserving machine learning forward. And that's what we're doing with TF Encrypted. So TF Encrypted is all about making this stuff accessible. So if you're not a cryptographer, then you don't have to understand the protocols we just saw. You can just start using this stuff directly in TensorFlow. And to give you an idea of that, you guys already know what TensorFlow is. To give you an idea of how that works, this is basically how you build a TF Encrypted application. So at the bottom here, we have ordinary TensorFlow, where we're using sometimes the distributed execution engine. We're using the optimized tensor operations, some of the machine learning layers. You build your application on top where you can mix both ordinary computations and encrypted computations. So if you want to do stuff on data locally, before sending it into the encrypted computation, you can use TensorFlow for that, and it integrates nicely. Then we have TF Encrypted over here, where we're using some of these secure computation protocols we just saw. We have various operations that you typically find, so matmols, RAILUs, sigmoids, and so on. And then we also, in the future at least, want to link to these third-party libraries that exist for other types of secure computation. So I already talked about secure sharing for MPC, but there's also things like homomorphic encryption and secure enclaves and so on. Okay, so to give you a quick example of how you're using TF Encrypted, let's look at the prediction example again. And this is our case here. So we now have a model owner here on the left that somehow generated weights for a model. He's going to send shares of those to the prediction service and the helper. The client is going to send shares of X. They're going to do a computation together, and then they're going to send back shares of the logic. So here we're using the MNIST example. The way you want to express that in TF Encrypted, if we look first at how it looks in ordinary TensorFlow, this is what we see. So we have some functions up here that just loads the disk from the weights from disk, that does some pre-processing on the input and so on. Then it defines a small model. Here we're using a small neural network, and then defines this predict operation that we can then execute in a normal session. Now, if we're using TF Encrypted instead, then this is what it looks like. And the first thing is we're now going to import both TensorFlow, because you can use both, and TF Encrypted. And the next thing is, instead of calling provide weights for the model directly, we're now annotating with this defined private input. And we're giving it a name, saying this is a function that has to be executed on the model owner, and he's the only one that's allowed to see these weights in plain text. So this means that the weights we now have here on the left are actually encrypted weights. These are the shared values that we saw before. And likewise for the prediction input, we're now saying this is a value that comes from the prediction client. And so you execute provide input on the prediction client locally using ordinary TensorFlow. When you're done with that, take the values, secret share them, and send them to the two helpers. And then the X we get out of that is an encrypted value. Then we can define the model as before. And likewise, we say for the prediction client, we now have an encrypted or secret shared logics. And now we can send them to the receive output, reconstruct there, and then call the normal TensorFlow to print the argmax. That's the only difference. Okay, so we can also use TensorBoard to inspect what's going on here. We can see that we have the prediction client is sending the input at the bottom. He's getting the output at the top. We have our two compute servers. So this is the cloud service and the helper in the middle doing the computation. And we also have the model owner at the very bottom providing the initial weights for the prediction. And then you can open up these. If you're using actual TensorBoard, you can open up these and you can see the further operations happening underneath. This is also a good way to make sure that you're not leaking any data, because TensorBoard will give you a clear illustration of who gets to see what data this way. We can also use local processing, as I said. So in our case, we're building a TF data pipeline to pre-process the images on the devices before we put them into the encrypted space. We can also do other things. So this was just a normal prediction, but we can also start to say, what if we had different data sources and they kind of want to combine the data for a prediction to give more nuances? We can also easily do that. So in this case, we have 3 prediction clients, one providing the age, one providing the gender, one providing the income. We start by sending the shares of the weights, then we send the shares of this data. We combine it on the prediction service. We do a computation and we send back a prediction for this particular customer. Okay, the way to do that in TF Encrypted, essentially just to say, oh, we're going to have 3 private inputs and then we just concatenate them and then we run as we did before. So in this case, we're using a linear model. And then, yeah, we're using a linear model, we define the output, and we send it back to the result receiver. And that's it. Another use case is training, of course. So how can you train on the data without seeing it? The setup for that is we have some data owner over here that's providing the training data. He sends shares of this to the training service and, again, a helper. They run a protocol together, arrive at some shares of weights that they can then send to the prediction service. Now remember that the data owner, the training data owner, is also allowed to be part of this process. So instead of using a helper here, we can also say, well, what if he continues to be the helper in this case? Then he controls how the training is done on the data. And of course that continues as well. So if he wants to be part of the prediction service as well, he can also say, well, I'm going to be the one that helps you run these private predictions. So he can kind of control the usage all the way down to the prediction service if he wants to. To express that in TF Encrypted is also straightforward. So here we're just using a simple logistic regression model. We have some upcoming work where this is closer built into the system. This is just a slightly older example. Here you're defining your training data. You can fit the model to this data and then evaluate it. In our case, we want the result of the evaluation to be sent back to the data owner. So he's the only one that gets to see how much he helped improve the model by contributing his data. The overall computation looks like this. So again, we can go in and we can inspect, saying, okay, for the training process, the data owner was involved. And then afterwards, the model owner got to see only the results of the computation. And then finally, we can also do joint training. So we can have several parties coming together, training on their joint data, but without leaking any of this or revealing any of this data to the other parties. So let's say we have two experts or specialists in this case. They each have a training set. They now send shares of this training set to each other. They do a computation together and they arrive at some weights for a model. Expressing this in TF Encrypted is also straightforward. We have two data owners in this case. We say we want this computation to happen between these two, and we just concatenate the data sets as we did before. Okay, so finally, the last example is around federated learning. Some of you may have heard of as well. The idea of federated learning is we have some data owners again here on the left. We have a model owner on the right, and now the model owner wants to use the data of the data owners to improve his model. Now, instead of putting everything into the encrypted space, federated learning works by sending essentially the current version of the model to the data owners. The data owner runs a local step to generate an update or gradients for the weights, and then they send that back to the data or to the model owner. As a way of getting privacy, we can say that none of these model updates are allowed to be leaked on their own. So we want to aggregate this model update before revealing it to the model owner, and using, in this case, a cloud service with a helper as well. So in other words, we can ask these three to share the model updates they have. We can compute some kind of aggregate of these updates and then only send a single aggregated update back to the model owner. This is a typical federated learning using secure aggregation system or setup. If you want to express that using TF Encrypted, it's also relatively straightforward. The first thing we do is we say we have some model owner, we have a data owner. We ask each data owner to build a training model on their own devices. Then we ask each data owner to compute the gradients, so to get the model updates. We compute an aggregate, so in this case, we're just taking the mean. Then we're sending the mean back to the model owner, and then we execute it for a certain number of iterations at the bottom. Again, if we look in TensorBoard, we can see what this looks like. So we have the model owner owning the parameters and taking care of the output. So the output here is where the model updates are revealed and applied to the current version of the model. We have the data owners in the middle, providing doing the local computation on their own training sets, and then having the compute service in the middle. So that's the service and the helper doing the aggregation. If we open these things up, we can see that inside each data owner, we're just using an ordinary TensorFlow computation using a Keras optimizer. Okay, so we have a quick roadmap. I'll skip through really quickly. We want to have high-level APIs. We already saw some hints of that, where we have Keras. What does that mean when you have your own encrypted data? We're going to expose some pre-trained models. That's this concept of own data. We want to have a tight integration. So TensorFlow 2.0 is coming up. We're working on supporting that. We want to integrate with TensorFlow Privacy, another project from Google that you may have heard of, and TF Federated as well. We want to support these third-party libraries to give more options. And then finally, we can always improve performance. To quickly wrap up, what I wanted to show here was that you can compute on data in encrypted form without being able to decrypt. You can, by having this privacy-preserving machine learning, you can mitigate some bottlenecks that might otherwise exist, and you can enable access to sensitive data. Secure computation is all about distributing trusted control, and for whatever trying to mitigate bottlenecks you use case. You need to have kind of adaptations from both sides, so being in a common framework is essential. And TF Encrypted is really about making this easy to use. There's a few resources here on GitHub, and otherwise I'll say thank you.
All right, thank you very much, Morten. That was a lot of content here. Great presentation. We do have a couple of questions here in the chat window. So one came in earlier around the performance impact. So Vikram says the encryption mechanism will slow down the whole ML process. And obviously in machine learning, we want to process a large data set. So maybe you can comment on the performance impact there.
Oh yeah, so there's definitely a performance overhead. And that's also one of the reasons why we think that you have to be in TensorFlow where you can start to mix these things. So you can say if there's some things you can do locally on the data in plain text, then do that, and then only have only move part of the process into the encrypted space. For instance, with federated learning, where you're doing a lot in the plain text. We are trying to minimize this overhead. There's a large research field working on this as well. I think currently we say something like 2 orders of magnitude is a slowdown when you move it into the encrypted space. And this just keeps improving all the time, of course.
Okay, great. And one more question, is TensorFlow Encrypted coming with TensorFlow 2.0 or also available in 1.9?
So right now we're only supporting 1.x, but we are working on upgrading this to TensorFlow 2.0.
Okay, great. All right, I think that were the questions so far. Slides and recording will be shared, yes. It's shared via python.ai/community. And let me see, are there any more questions? Please post them to the chat window. I see Jose had his hand raised. Do you have a question? You can unmute yourself in case. And if not, okay. So thank you very much for the presenters, Dave and Morten. Really interesting talks. Unfortunately, we do have to push out our third talk today, but there's a workshop coming up next Saturday in Santa Clara, where we will focus more on image recognition using PyTorch, TensorFlow, and Redis. So please check out, if you haven't seen it, the Meetup group, and you can register there for the workshop on Saturday in Santa Clara. And with that, we're giving everyone back a little bit of time today. Have a good week, and thanks again, Dave and Morten, and hope to talk to you all soon. Thank you. Bye-bye.